generate all that data, look at different stacking sequences, I mean, different percentage of number of plies at different orientations, and different curing conditions. And so you have an automated CAD approach being developed in the project to build all these surfaces, and then here, for example, a sample of different possible orientations, build sampling through Latin hypercube, and build a surrogate model using different surrogates. Here, for the moment, we've looked at Kriging approaches, which is, works well with deterministic problems. And for the moment, we still have to work on this, you see that at some locations, there's a cross-correlation analysis. Some locations you have very good predictions. At other locations, especially for larger distortions, the quality of the surrogate models built with the Kriging method are not yet ideal. So we have to work on more explainable or physics-oriented surrogates. In damage simulation, we want to predict nonlinear behavior, and so Hexagon, University of Liège, and Neji are working on recurrent, very specific recurrent neural networks that will be, let's say, mesh dependent or size mesh independent or size independent, and be able to predict the response at different points of the loading curve. And you see the predictions between the full, let's say, multi-scale finite element simulation. So you have a big so it's what the FE2 model you call here, that requires simulating first the macro scale and then at each point the micro scale. This can take up a lot of time. And so what's being done is, okay, it takes time, but generating data on to train the micro scale, and using this training, you can make very fast evaluations at the macro scale. So that, let's say, gives a quick overview of what's being done in the project. As I said, we're halfway, so we're still working and generating data. But further on, okay, we want to work on the building of the hybrid testing pyramid, and feed, both for manufacturing and for testing, the micro scale towards the macro scale simulations. So just an idea of what's coming up. So we have, like other projects, regular bi-monthly meetings, but advisory boards every year. And in 2025, more 2026, we have workshops during conferences that will be organized, one more on HPC, the other one on industrial applications, and finally, also one more on physics, so damage and manufacturing. I think that brings me to the end of my presentation. Thanks a lot for your attention, and I look forward to the discussions we'll have. Thanks.
So do we have any questions for David?
Just didn't catch what you name hybrid.
It was a lot.
So it's just simulation and experiments?
I didn't cover that part, but so Technalia is looking also at not printed sensors, but integrated sensors too. And so the idea is using data from simulations, but also tests to fuse the data. Exactly.
The core of the project is to simulate small scale and then
see how we can train it and if it can be used correctly at the larger scale. Exactly.
Any other question? No? So thank you again, David.
Thank you.
And now we are changing not only the country of the presenter, that he comes from France, from the ENS Paris-Saclay, but we are changing the program, because until now we hear about projects funded by Horizon Europe, and now we have an ERC project named Dream On. So let's give the floor to Ludovic Chamoin, who is going to present this project.
Thank you. Just to check. Done. Okay. Yeah, perfect. Okay, thank you. Thank you very much for the invitation, and I'm happy to be there and to see the connection between my work and all that has been presented. I have new ideas now, so it's very good for that. So I'm going to present a project which is mainly based on, so you're still on damage control and things like this, as the main topic of what has been presented before, but more on the numerical sides and methodologies with data simulation and control. So that's the overall idea of the project. So I'm going to be fast on that because that's a classical context that you have seen already, but just to mention that we really want to couple a physics structure equipped with sensors, and in this project we use optic fiber sensors, with a digital twin, and the idea is to really be smart in the way we build this digital twin, and the way we adapt it on the fly to be able to do real-time, robust, and very accurate the damage estimation and control. So that's the overall idea, okay? So, having that in mind, we are faced with some difficulties which are complex, because in practice, if we want to do that, you need to address very non-linear, very large systems, so it's not very, it's far from real-time computation in practice. You are in an uncertain environment because you don't know really nice the boundary conditions, the modeling, data are noisy, and so on. So you have a lot of difficulties with that. But still, we want to do something which is robust in that sense, and I will explain it in a little bit after how I do it. Okay. So to do it, we use several numerical techniques, and in particular hybrid twins, and in the sense that I think you hear it, Nazi. And we also use some other tools. I will give very little equation, one or two, just to explain the concepts, but I will try to do it very in a very easy way. Okay, so we use advanced sampling in terms of optic fibers, as I said. We use hybrid modeling and also very advanced numerical approaches to be able to be both real-time, robust, and accurate. Okay, so that's the overall idea of the project. There are three main blocks, which are the three colors. One in blue is more on data assimilation, and we'll start with that. One is more on bias correction, and we use AI to do that, so that's the hybrid way. And one in orange, which is on the control. We use model predictive control to also have the feedback on the application to be able to control the damage in practice. That's the proof of concept of the project. We want to do that, so we are close to be there because we already have many tools to do that. The idea is to really have a lab experiments where you see that the control of the structure, structure is a small red part, is performed with a steward platform. And the interest of this is that you can control multi-axial loading, and the idea is really to do dynamic control to be able to have a structure which remains in the safety domain, and starting from a given damage area, you want to explore what could be applied or not to the structure. That's the overall idea. Okay, so let's start with the first data simulation strategy. That's the main concept of the project. That's my equation. And the idea is to use these tools. That's a tool which was developed for inverse analysis from a long time ago. But for us, it's very interesting because that's a natural way to see data simulation, in my opinion, where you're going to split what you know is reliable on your problem, balance equations, and some other physics you know, and you really lean on the modeling that has been performed by engineers for a long time ago. And all that you don't really know, boundary conditions, the material behavior, the measurement value, because there is noise, you are going to release them and to try to satisfy them at best during the procedure. So that gives rise to this formulation, what we call the MCR in practice, modified quantitative relation error. It's an optimization problem. But at the end of the day, you end up with a new estimation of your system, here in practice from the mechanics of displacement, stress, and so on. Something which is hybrid, because this minimization, this optimization, will give you a state which doesn't come from physics, which doesn't come from data, but which comes something in between, that satisfies the both at best with your a priori information. That's the main concept which is behind this approach. There are many nice features for this, which have been developed and explained numerically from a long time ago, but that's the thing we use. Of course, if we want to do real time, if we want to do control, we have to add things to this, but that's the main brick, the main hybrid modeling technique. So it is also interesting because it enables to adapt the model and to select the model which is going to be consistent with the data. And also it's important in terms of data adaptation. Here I simply show an example with image correlation. You have a field of data, of kinematic data, and you can select by a given procedure from this term in the MCRE. You have a term here which acts as a modeling error term, and it's very important for adaptation. You can on the fly take a model which is more or less rich depending on the data you have. And this, for instance, for this image correlation, you can pick among a list of model with increasing complexity, the one which is going to be adapted to what you want to show. So if you normalize everything, the perfect model should be with an error which is about 1. That means that you are consistent between the data and the modeling. So it's very helpful to select the model on the fly. So at the beginning to have something which is quite crude, and when there is damage coming in, you are going to increase the complexity to catch locally what is coming, what is appearing. That's the idea. Okay, so to go now sequentially in time, we complement all this framework with data assimilation with Kalman filtering. So we use a sequential version of Kalman filtering, in which the MCRE is used to more or less change the observation operator. Okay, and I will not go into the detail, but that's the idea. So we couple these two techniques, and this has been done already in several projects. And I just want to mention one which is quite interesting for me. That's one which was driven by CEA in France. The idea was to control the checking table tests they have, because when they perform checking table tests, they have a building on the table, which is going to damage. That change the dynamics of the building, and that, of course, change the control you have to apply, because the control is based on the first eigenfrequency of the systems. And of course, if damage appears, that will change the eigenfrequency. So the goal was to catch how the building is going to damage in real time. And then we use this data simulation strategy, Kalman filtering plus MCRE, that we call MDKF in practice. And that's what you get. So we work in the dynamic framework, in the frequency framework with classical tools. And then we were able in real time, so real time here means about 1 second between several data simulation sequence, to recover the state of the system, the damage in practice in each part of the building, and then to compute the few first eigenfrequencies which are changing in practice. And then you see that during the tests, you have some zones, because the test is increasingly damaging the structure. You are able to catch where the damage is going to occur, how it's going to evolve, and then you are going to adapt in real time the control you have to apply to the checking table to avoid some weird situation or even some unstable tests. Okay, so we did that 2 years ago. So we have all this loop between the data simulation and the control. Here the control is a simple LQP controller. It's very simple in terms of control, but you are able to go from a non-stable test to a stable test simply by assimilating data and recovering the damage state in real time. Okay? So that was the first thing. So of course in the ERC project we do that, but now with optic fibers and with structure which are a little bit more complex. So we use here optic fiber in terms of Rayleigh backscattering. It's not Bragg, it's something different, but still. So we are able to put that in some sense, in some materials. We use concrete, we use composites, and so on. And then we are able to adapt to use this sequential adaptation like this. We have some other topics, and I will have time to detail that, but we use also optic fibers optimization in terms of position. Okay, so we use tools to do that. It's a very numerical optimization part. We also adaptation in the sense of how we represent the damage. So we play with the meshes, how we parameterize the damage in practice. So everything which is behind there, the goal is really to be fast in the online computation and online assimilation. Okay, so just to show you, the video is to show you that we manufacture everything. So we start, we put the fibers, and we manufacture from the beginning the structure. One word about the learning, where AI comes in. It naturally comes in because, as I said, you release the behavior. And what we are going to do with this MCRE, we are going to learn the behavior now. If you don't have the list of complexity I defined before, you can learn the behavior. And learning the behavior means learning the potential, the thermodynamic potentials that are going to define this behavior. which are well known, and that's where physics come in. You want the potential to be convex, so you are going to use input convex neural networks, and you learn state and evolution behavior that define how the damage should occur and should propagate in time. Okay, so I don't have time to explain everything, but still we use this MCRE framework as a cost function, as a loss function in the learning. So we did that for state equation. We did that for evolution law. Very important to know how the damage is going to propagate. And last point is on the control. We also have actions on control, because now that you have access to your updated model, you know where you are in terms of damage, you know how you're going to propagate. You need to know what should be the control you have to apply at the next step to be able to control the overall damage of your structure. And for that, you use MPC in a way that, in order to be fast again, we use MPC in a neural network way. So we train a neural network to learn the response of an MPC controller, because MPC, you have to solve an optimization at each system step, so it can be costly. So we learn here how it should respond, and of course, it's compatible with real time at the end of the day. Okay? So just to show you as a final word, where we are now, we are there. So we have built this integrated device where you have here everything. You have the sensors in terms of optic fibers with the integrator, which is at the bottom there. You have the hexapod, the CWAT platform, which is going to load and to control. You have the part, which is in practice a small wind turbine blade. And then you are going to we control that in practice, putting everything together, and that's where we are now. And at the end of the project, we hope to have something in a larger scale. But at the moment, the size is about 1 meter for the structure. Okay, so that's at the end of the presentation. A few references if you want to go in details. And with that, I thank you for your attention.
Let's see if there are any questions for you. Yes, Helena.
For the identity tracking,
Yeah.
was it with non-excitation or with random excitation?
With what?
Random or non-excitation?
Oh, it's none. It's not. Actually, what you apply, the idea of the control. Oops, sorry. The idea of the control is really to apply to the structure a real signal, a real seismic signal. And of course, if your control is not correct, what the building will see is something which is completely different from what you would like to see. So the signal is given. The input of the checking table, and of course you want the output to see the same thing.
And the other question is for the physics augmented neural network.
Yeah.
In which way does physics augment it?
It's segmented in several ways. The main one is because you are going to enforce convexity, so you are consistent with thermodynamics. Okay, so with input convex neural networks, you are sure that the dissipation is positive in practice. But it's also augmented in the sense that, as I said before, in the MCRE, you are going to split what is reliable, what is not reliable, and everything which is reliable, in particular the equilibrium, will be enforced strongly in the process. And that's enabled to do what we call unsupervised learning, because we learn only from kinematic data. The stress, for instance, is automatically computed from this property. You don't need to have supervised learning with kinematic and static data together. You only need kinematic data because stress or everything related to force, to statics, will be recovered from equilibrium, because you have to enforce equilibrium. So that's the main advantage, because of course, in practice, you only have access to other global loading, but you don't have access to local stress. You cannot measure that. So you need this kind of unsupervised approach.
Any other questions? Okay, so thank you very much. Now, for the next presenter, you already know him, and he is Nikos from SYNTHESITES, that he is going to introduce the Turbo project, in which he is also a partner. So thank you very much, Nikos.
Yeah.
Yeah, we are arranging.
Why it starts from just close. Just close the.
Well, typical technical problems that event has. Thank you.
Thank you. So I was thinking about the sister projects, and that means that if we are sister projects, our mother is the European Commission, which is a bit scary, I would say. But anyway, so for us, for Synthesites, it's very nice that we are participating in two projects where our business lies, which is both aerospace, MORPHO in aerospace, and Turbo in wind turbines. So I would say the concept of this project is very similar to MORPHO, but of course the details change everything, and the application change a lot. So this project is in the zero waste area of the Horizon 2020, I think. The consortium has, I'm not sure how many partners, 2, 4, 6, 8 partners from Europe, and then it was the intermediate period where the British partners were like associated partners. And actually, during the, because now we are on the 29th month of the project, and across the period, we lost 2 partners. So we changed a little bit the structure of the project in order to deal with these changes. So as I said, the idea, the key objectives are very similar to MORPHO. Again, we have a digital twin, we have simulations, we have sensors, inline monitor for our sensors, and together with NDT. And the idea, of course, is to minimize the waste in the production of wind blades, in this case, but in general, it's something that can be applied to many other composite structures. As I said, we are 10 partners. You can see that ESI is also involved for the simulations, flow simulations. DTU is the coordinator of the project. DTU in Copenhagen, and they are involved in several work packages. Siemens Gamesa is the main end user and provides all the data for the application and for the demonstration. National Composite Center is involved both in for the flow monitoring, but also for the NDT inspection. CPI developing wireless resin arrival sensors and temperature sensors. We are providing our sensors and the online TG technology, and Norbliss are more involved for the mid-infrared inspection of the blades after production. And then we have University of Valencia, who are developing the machine learning tools, and Arditech, who is in charge of the life cycle analysis. So again, we have simulations of the process, mainly of the flow. Actually, in this case, it's quite particular because Siemens is the only wind blade manufacturer who is producing the blades in one shot. So you have a mold that could be more than 100 meters. Actually, their most recent blade is 115 meters. And then they infuse this part in one shot. And this is quite unique for wind blades because normally all the other OEMs, they are just infusing the 2 parts, the upper and the lower part, and then they bond them together. So it's quite challenging process, And at the moment, they don't use any sensors, so it was a very nice opportunity to start working in this area. So besides the simulations, we have developed further our technology in order to deal with the different specifications for wind energy. And also, this is also very interesting, is that now CPI has developed some wireless sensors which they can be placed outside of the mold, and they can sense resin arrival and temperature without modifying the mold, let's say. But of course, this is something that we need to validate in real conditions. NDT, mainly for the coatings. As I said, there's a mid-infrared optical tomography OCT scanner, which has been developed by DTU and also in collaboration with NCC. They have been testing that, and we are going also to apply this in real conditions with Siemens in Aalborg. Machine learning, again, perhaps it's a different approach. I'm not sure how it's related to our approach. Machine learning is for both the NDT inspection and the flow simulations. As I said, this is the NDT capabilities being tested now at NCC. Of course, we are building also a platform which can gather all the data from the sensors, the simulations, and can really retrieve everything, connecting it to the machine learning part, and trying at the end to control the injection process. This is the ultimate target. So we want to improve the manufacturing, we want to reduce the waste, and this is something that remains to be proved. We have the first, let's say we call it baseline test, will be in 2 weeks. We are going to, Siemens is going to infuse 15-meter section of the blade, and we are going to have sensors in order to check and to monitor the process and have it as a baseline for the final demonstrator where we are going to apply also the control. Of course, we take into consideration sustainability assessment and life cycle analysis and management. This is the location of the Siemens in Aalborg. They manufacture, as I said, blades up to 115 meters offshore blades. And we are going to apply to make the final demonstrator here, I think, at the end of this year. I think that's it from the turbo. Thank you for your attention.
Thank you, Nikos. And do we have any questions for him? No? We have one.
I saw you're talking about the new sensors, so wireless sensors. The idea is to be able to put it in the part but have no contact with the, say, external monitoring. You don't have any wire going from the...
Our sensors are mainly wired sensors.
Okay.
But CPI has developed the wireless sensors.
And yeah, and that's mostly for, say, non-metallic mold, or
Yes.
work too with the metallic?
Yes.
Any other questions?
And for lower temperature, it's not for our space. It's
No, so we can dismiss Nikos. Thank you very much
Thank you.
again. And we have now the final presentation of this sister project section of our agenda today. And we have, this is a national funded project. So we have the University of Vigo and Alejandro Gómez-San-Juan to make this final presentation and introduce you the TAMC project. So welcome, Alejandro.
Thank you. Okay, hello, good afternoon. Well, first of all, thank you for MORPHO project for inviting us to be here to listen these really insightful presentations and to explain ours. Okay, so my name is Alejandro Gómez. I am a professor from Vigo University, specialized in thermal and structural analysis of space systems. Okay, so I am from the Aerospace Technology Research Group. Sorry, is there?
Yeah, what is it? It's not in the...
Oh, it's in the booth. Ah, okay, thank you. Sorry. Down? Okay. Okay, so as we are a very young group, so I will take 1.5 minutes just to tell you who we are. Vigo University has experience in space systems, in sending satellites. Okay, that's actually the first Spanish CubeSat was sent by the PI of our group, Fernando Aguado. Okay, but the actual aerospace technology research group came with the foundation of the Aerospace Engineering School here in Vigo, which has 7 years now, so it's kind of a young school. Okay, so this group was joined by some professors from other universities. Okay, so that we started working there, and well, as you can see, we've had some quite busy latest years going deeper into this area. Okay, of space telescopes. Okay, so here you can see some of our projects, mainly with the Astrophysical Institute of the Canary Islands, okay, which is a world-renowned organization. Okay, so I'm going to talk you about, well, this is, okay, this really nice people is who we are, okay, small team. And, okay, so I'm going to talk you about our project, which is the application of uncertainty calculation to the thermoelastic models of space telescopes. Okay, so the thing is, as you probably are aware of, thermoelastics is a huge thing with space telescopes. You have, for example, the Hubble Space Telescope had a thermoelastic unexpected problem called thermal snap, that when it passed from the light to the shadow, or when from the shadow to the light during the eclipse occultation, it's not so stiff as solar panels, had a thermal snap, and it messed with the control system, so it lost stability. Okay, Hubble could be repaired and reserviced, and it had new solar panels. Okay, or for example, in the development of the Herschel Space Telescope, there was a large uncertainty with the coefficient of thermal expansion of the materials. Okay, and also they had a blind telescope, and they had a really huge problem that luckily they could solve here on Earth. Okay, the thing is, there are always unexpected problems, and you hear maybe of the most famous, but if things are not too wild, these don't come out to the public. So what we think is this is kind of a very complicated problem because it involves different fields, and usually, for example, when you can have multi-physics like in ANSYS, but in the space sector in Europe you cannot really do that because the software that the European Space Agency approves is ESATAN, which has a specific mathematical formulation, and usually the calculations are made with finite element models, such as like Nastran. So in this problem, which is actually a couple problem from the beginning till the end, you have one mathematical formulation for the thermal analysis, another mathematical formulation for the structural analysis. Then you have something in the middle, which you have to paste in some sort of way the temperatures from one model to the others. And also, these two fields are usually done by separate teams. Okay, that sometimes they have some good relationship, other they don't have such good relationship. So it's kind of a complicated problem. So we wanted to try to make something to be able to homogenize all these problems. So we use uncertainty calculation. So, well, as you very quick here, as you know, usually when you have a parameter, it really never has its expected value. Okay, so we usually have the expected value is the mean, and we have an actual value, and if we've done our homework, it should be within an uncertainty range. Okay, and that would be for all the parameters of our model. So in the end, in any model, you have some performance parameters and some design parameters. Okay, and once the performance parameters will be function of these design parameters. So in the end, we can make our mathematical model work as a black box. So we insert this the probability distributions of our design parameters, and we obtain our performance parameter with some uncertainty. Okay, so actually this is something usually done. For those of you who are most familiar with the engineering structural work, you may know the safety factors or the uncertainty margins. Okay, those are one of the most extended ways, okay, consisting of fixed factors based on experience, but you have also other type of methods. Okay, so in our project, we use two type of methods. One are the one-at-a-time methods, in which you make a variation of one parameter each time. Okay, and then you compute the uncertainty as some sort of combination of these individual uncertainties. Okay, and also we have Monte Carlo simulations. OAT methods are fast. But they might miss some quite some things because they only actuate one parameter at a time, while Monte Carlo simulations are not so fast, but they take into account much more things. Okay, so this is how we do it in the thermoelastic problem. Okay, so as you can see, we have some thermal parameters. Okay, we have then that will give a temperature uncertainty. We have also some uncertainty from the thermal mapping process. We have also some structural uncertainty. Okay, and in this project we would stop here, but actually we are working on another project with the European Space Agency in which we work on this last bit, which is the optical uncertainties. So we can go directly to the wavefront error or other figures of merit from the optical system. Okay, so as you can see, the problem is quite complicated because we have to couple of these things, and we wanted to develop a methodology which was really simple and that could be applied almost by anyone in the space industry in Europe without a lot of effort. Okay, so we are by the middle of our project. Okay, what we have been able to develop now are these one-at-a-time methods and their application. Okay, we have two methods: the statistical error analysis, which is the classic uncertainty error calculation from, I guess everybody here will have gone in university through their lab practical assignments, okay, and you had to do your calculation of errors. Okay, so it's pretty much this. This is it's very simple method, but it's really interesting because for each of the parameters you have two parts. Okay, you have here a sensitivity coefficient, okay, and here you have the uncertainty of the parameter, and the uncertainty on the performance parameter is sensitivity coefficients times the uncertainty of the design parameter. So you can you have actually a lot of information, okay, and Rosenbluth, it's a little more complex, okay, will not delve into details here, but you have similar information, and also Rosenbluth uses more runs, and you can get information on the asymmetry of the behavior, okay, of the performance parameter with each of the design parameters. Okay, so all this, what leads us to. So you can see here a case of study. This is an Earth observation telescope from the Astrophysical Institute of the Canary Islands. Okay, and what we have been able to do, okay, is we use our uncertainty method calculation with the most severe thermoelastic cases, and we are able to obtain not only the global uncertainty, but also the parameters that most influentiate this uncertainty. Okay, so this in part is due to the uncertainty of these design parameters, but it's also due to the sensitivity. So in one simple map, we have an X-ray of all the most important parts of the structure, and that parts that we should take into account to build and design our system. For example, we can see here, I'll not go into all the parameters, but half of the uncertainty is due to the thermal problem. It's due to the infrared emission from Earth. Okay, and there's nothing that we can do about that because it's an Earth observation telescope. So we know that we will have to live with this uncertainty in our results. But on the other hand, we see here, okay, a number of parameters. Okay, so now we can see that a large part of our uncertainty and due to our possible loss of performance is here in these rods, okay, and we can go directly to the constant of thermal expansion of these rods, okay, and we can act on that, and we can say, okay, so initially we wanted to make a cheap design, but now we cannot go for that because it's really hindering our performance, so we can go and change them to titanium. And also with the different parts of the mechanical assembly. Here that you can see, it's the two performance parameter. One, it's the decentering, okay, of between the two mirrors. This is a Ritchie-Chrétien telescope that has a main mirror and a secondary mirror, and then a focal plane behind. For example, this is the distance between the mirrors. So you can have here the requirement, the result, and the uncertainty, and the decomposition of all this. So we can use this during the design process, but we can also know with this process which parts are the most prone to influentiate our design. And for example, if we have to do a structural thermal model and engineering model for testing, we can directly go to represent those parameters that will give the largest contribution to uncertainty, okay, and invest our time and money and effort in that, and be more flexible with the other parts. So it's a really nice, it's a simple but nice tool to help with the design. Also, just finishing now, ESA was very interested in our methodology. So we have been lately in collaboration with them. We are contributing to the second version of the European guidelines for thermoelastic verification to help to put these methods inside. And also, our methodology has strong synergies with the latest developments by ESA. Okay, because for example, this that you can see in colors are the different areas from a tool from ESA that detects the parts that most influentiate. And with ESA tools, you can detect the parts, and with our tool you can laser focus on the different parameters of those tools that will influentiate this behavior. So just to finish, it's a really simple tool, and it can be useful for improving the design process. In the end, we would like that a large part of European space community, through the implementation in the guidelines, will be able to use this method. And it can greatly assist design process, testing, planning, and everything. Up to now, we have been using the OAT methods, and we think we have quite promising results already. And the next step would be to use the Monte Carlo simulation methods that can put in evidence this combination between parameters that can be quite a problem at some times. For example, if you have a telescope, maybe the distance between the two mirrors, it might be a problem itself, but you have certain restrictions. But if you have only a small deviation in the position of the optical axis, okay, a small deviation on the distance will have a large effect. So some parameters have strong interaction between them. So that will be the next and last part of our project. Oh, sorry, I didn't put a closing slide. Oh, well, that would be all. Thank you for your attention very much. Any questions?
Alejandro, do we have any questions for him? No? No curious at all? Okay, so thank you very much. And now we have the break for lunch, but I wanted to remind you to post about this event. We have our hashtag MORPHOFINAL everywhere, so so you cannot miss that. I wanted also to remind you about our wonderful planes that we have, so you can take some pictures to remember about this event. And I will also say that while we are taking pictures and recording this, we will be posting a video summarizing the event, and we will be posting some pictures of the event. And I will post them on the project website, so you will visit and get me more very, very good statistics for the reporting. So be attentive, it will be updated in the website tomorrow already. Okay, so now enjoy the poster session, enjoy the photo call, and the lunch, of course. Thank you very much.